Section 3.5, conditional statements and their converse. So consider the following two statements. If Brianna is texting, then she's using a cell phone. If she's using a cell phone, then she's texting. How do these statements relate, and are they both true? Okay, they're related because we have if texting, then cell phone, and here we have if cell phone, then texting. These are called conditional statements, if then. There's a hypothesis and a conclusion. So we switch the hypothesis and the conclusion. Are they true? If she's texting, is she using a cell phone? Yes. Now I know there's a little bit of a loophole. I know there's ways you can text on a computer and an iPad. If they're using a cell phone, is she texting? Not necessarily. She could be using a cell phone to be on the internet. She could be using it to talk to someone, believe it or not, listen to music. Okay, so we're talking about if-then statements. So James and Gregory like to play soccer regardless of the weather. Their coach made this conditional statement about today's practice. If it's raining, then we're going to practice indoors. Okay? And what we're going to do is we're going to decide what the hypothesis and the conclusion. So the hypothesis is raining outside. And the conclusion, practice indoors. What we're going to do is we're going to set up something called a truth. Okay, and first of all, I'm going to call this P and this Q. And the table is going to look something like this. P, Q, and P, then Q. Okay, so if P is true and Q is true, so it's raining, we practiced outside, is if P then Q true? Yes. Okay, if this is false and false, so it was not raining, we did not practice indoors. Is this still true? P then Q, if it rains, we practice indoors? Yeah, that's definitely true. If this was false true, so if it was not raining and we practiced indoors, is this statement true? If raining, then we'll practice indoors. So it's not raining, but we practiced indoors. That's still true, right? If raining, then we practice indoors. That still followed that. Okay, so if it was raining and we didn't practice indoors, so it rained, we didn't practice indoors. If rain, practice indoors? No, this is no longer false. So that is my truth table for this conditional statement. Okay, so verify when the statement is true and when it's false. It's true in these three cases and it's false in this case. So in other words, this conditional statement is true all of the time except for when the hypothesis is true and the conclusion is false. Okay, here's another way to look at this statement. Verify when it's true or false. We can do a Venn diagram. So if raining, then we practice indoors. Okay, so what that means is this would be raining. This would be practice indoors, and this would be everything else. So if it's raining, you're indoors. You could also be indoors for another reason. If it was snowing, if they were planting grass, lots of reasons, okay? So it's the only reason it's not true is if it was raining and you practiced outside. That would be the only case that this would not be true. So a couple ways, a truth table or a Venn diagram. Recall the coach's statement, if it's raining outside, then we will practice indoors. Is the converse of this statement true or false, and justify your decision? Converse means that we are going to switch the hypothesis and the conclusion. Okay, so let's look what they did here. Is it true? So the converse, if we practice indoors, then it's raining outside. And he said, well, let's say that this part is true. If we practice indoors is true, we could be practicing indoors because the soccer field is under repair. not because it's raining. This counter example proves that the converse of the coach's statement is false. So all you need is one counter example, and then you've proven something is false. Now we're going to look at something called biconditional. And biconditional means that a statement and its converse is true. In logical notation, a biconditional is written as P if and only if Q. And the way we write that too is we could write it P instead of just PQ, there's an arrow on both sides. P if Q and Q if P. So regular and converse. Okay, here's an example. The statement is if a number is even, then it's divisible by true. The converse is if a number is divisible by 2, then it's even. The biconditional statement is a number is even if and only if it's divisible by 2. So here's an example. Sena told her friend, if you are north of latitude 60, you can experience over 18.8 hours of daylight. Is her statement true? Write the converse. Is that true? Sorry guys, there's band going on and they are moving chairs and I don't know if you can hear it, but I sure can. Okay. The southern borders of Yukon Northwest Territories and Nunavut lie along this latitude. On an hours of daylight map, the maximum hours of daylight in this latitude is 1853. Let P represent this hypothesis and Q is the conclusion. So if P, then Q. If P, then Q. That's true. Now let's look at the other thing. If Q, then P. That's also true because I assume that the new hypothesis, you experience over 18 hours of daylight. This means you are north. This new conclusion is also true. So that is also true. So since we have that P, then Q, and Q, then P, therefore P, if and only if Q is true. That is called biconditional. And I know this question was a little confusing because some of you might not have that information that those two things are biconditional, but hopefully the examples I give will be more clear. Okay, just to summarize everything, a conditional statement has a hypothesis P and a conclusion P. If P, then Q, P implies Q, P arrow Q. To write the converse, we simply switch P and Q. Conditional statement is either true or false. A truth table for P then Q looks like this. A conditional statement is false only when the hypothesis is true and the conclusion is false. It's the only way we get a false. Otherwise, the conditional statement is true, even with the hypothesis false. You can represent this also using a Venn diagram, with the inner oval representing the hypothesis and the outer oval representing the conclusion. The statement P implies Q's mean that P is a subset of Q's. This is how this connects to what we've been doing. Only one counterexample is needed to show that a conditional statement is false. If a conditional statement and its converse are true, you can combine them to create a biconditional using the phrase if and only if, and the notation is a double arrow. Don't worry if you just do a single. Sorry, I meant double in terms of the heads of the arrows. Don't worry about the two lines there. I generally only do one line because it's less work.